What specific problem does your proposed method address in the context of reinforcement learning for fine-tuning large language models, particularly with respect to mathematical reasoning tasks?
Our proposed method addresses the challenge of effectively fine-tuning large language models, LLMs, using reinforcement learning, RL, in the context of mathematical reasoning tasks, specifically by focusing on sample selection and the handling of negative samples. We find that traditional RL methods, such as GRPO, which utilize both positive and negative samples, can lead to high variance and misleading gradients that negatively impact learning. In contrast, our method, Reinforce-Reg, selectively filters out prompts with entirely correct or incorrect responses, thereby maintaining a focus on high-quality samples and improving training stability. This approach not only achieves competitive performance compared to more complex methods, but also demonstrates faster convergence in early training stages. Ultimately, our findings highlight the importance of sample quality over algorithmic complexity in enhancing the reasoning capabilities of LLMs.
Can you explain in detail how the proposed reinforcement learning method, Reinforce-Reg, works? Illustrate the methodology step by step as outlined in your paper.
The proposed reinforcement learning method, Reinforce-Reg, operates through a systematic approach that emphasizes selective sample filtering to enhance performance in fine-tuning large language models, LLMs. The methodology consists of several key steps. 1. Sample collection. For each prompt, the model generates multiple candidate responses, similar to traditional reinforcement learning methods. However, Reinforce-Reg specifically focuses on filtering these responses based on their correctness. 2. Filtering mechanism. The method employs a rejection sampling strategy where it removes prompts that yield either all correct or all incorrect responses. This selective filtering is crucial as it mitigates the negative impact of low-quality samples, particularly those that are entirely incorrect, which can introduce high variance and misleading gradients during training. 3. Reward calculation. The remaining responses, which are neither fully correct nor fully incorrect, are then evaluated using a binary reward function. This function assigns rewards based on the quality of the responses, allowing the model to learn from the most informative samples. 4. Policy update. The model is fine-tuned by maximizing the log likelihood of the selected positive samples, effectively updating the policy based on the filtered dataset. This process ensures that the model learns from high-quality responses while avoiding the pitfalls of poor samples. 5. Performance evaluation. The Reinforce-Reg method is designed to maintain exploration and prevent distributional collapse, leading to competitive performance compared to more complex algorithms like GRPO. The results indicate that this approach achieves a balance between simplicity and effectiveness, demonstrating that careful sample selection is more critical than intricate algorithmic designs in reward-based LLM post-training. This structured approach allows Reinforce-Reg to leverage the strengths of reinforcement learning while minimizing the drawbacks associated with negative samples, ultimately leading to improved model performance.
Could you provide a simple example to demonstrate the inner workings of your algorithm, specifically focusing on how it filters prompts and selects which responses to keep for training?
Certainly. In our algorithm, specifically the RAFT approach, we begin by collecting a batch of prompts, say, x_1, x_2, l.dots, x_m. For each prompt, we generate n candidate responses, a_i1, a_i2, l.dots, a_in, and evaluate them using a binary reward function, rxa, which assigns a reward of 1 for correct responses and -1 for incorrect ones. During the data ranking step, we filter these responses by retaining only those with the highest reward, typically those with r=1. This results in a dataset, D, composed solely of positive samples, which are then used to fine-tune the model. For instance, if a prompt yields responses where only 1 is correct, that correct response is kept for training, while all incorrect responses are discarded, ensuring that the model learns from high-quality examples.
What are the theoretical advantages of using your proposed method compared to existing approaches like GRPO or RAFT? How does it enhance efficiency, accuracy, or convergence?
The proposed method, Reinforce Reg, offers several theoretical advantages over existing approaches like GRPO and RAFT. Firstly, it selectively filters out prompts with either all correct or all incorrect responses, which mitigates the negative impact of misleading gradients from incorrect samples that can dominate updates in traditional reinforce methods. This targeted sample selection enhances the model's learning efficiency by maintaining a more stable policy entropy, which is crucial for exploration and prevents distributional collapse. Additionally, Reinforce Reg achieves competitive performance with GRPO while simplifying the algorithmic design, as it does not rely on complex reward normalization techniques that have shown minimal impact. Finally, the method demonstrates superior KL efficiency, allowing for faster convergence during training, particularly in the early stages, which is a significant advantage over both GRPO and RAFT.
How did you validate your proposed method? Please describe the experimental design, metrics used for evaluation, and the datasets involved in your testing.
To validate our proposed method, we conducted experiments focusing on mathematical reasoning tasks using the Minimalist dataset, which contains approximately 860K math problems with labeled ground truth answers. We evaluated the model's reasoning abilities using benchmarks such as Math 500, Minerva Math, and Olympiad Bench, primarily employing the average accuracy metric, specifically average at 1/6, where we generated 16 responses per prompt. Our experimental design included comparing various algorithms, including RAFT, RAFT++, GRPO, and Reinforce, to assess their performance and convergence rates. We also performed ablation studies to isolate the effects of different design choices, such as the impact of negative samples and reward normalization on model performance. The results indicated that RAFT and its variant RAFT++ achieved competitive performance compared to more complex methods, with RAFT++ demonstrating faster early-stage convergence, but ultimately being surpassed by GRPO in later training stages.
What limitations or potential drawbacks does your proposed method have, particularly in comparison to more complex RL methods like GRPO and PPO? How might these limitations affect its applicability or performance?
The proposed method, particularly RAFT and its variant RAFT++, has notable limitations compared to more complex RL methods like GRPO and PPO. One significant drawback is that RAFT exclusively utilizes positive samples, which can lead to rapid policy entropy reduction and limit exploration, ultimately causing it to plateau in performance during later training stages. This lack of exploration may hinder the model's ability to generate diverse reasoning paths, as evidenced by RAFT++ being surpassed by GRPO in final accuracy, despite its faster early-stage convergence. Additionally, while GRPO benefits from the implicit filtering of harmful prompts through the use of negative samples, RAFT's reliance on positive samples alone may restrict its adaptability to various problem types, particularly those with incorrect responses. Consequently, these limitations could affect RAFT's overall performance and applicability in more complex reasoning tasks, where diverse exploration and robust sample selection are crucial for success.